My name is Jeremy Schulman. You can find me on Twitter as Network Automaniac. And in this presentation, I'm going to cover a network health monitoring system that I built at Major League Baseball so that we could understand the health of our optics throughout our baseball network. So what is an optics monitoring dashboard, and what is it that we're trying to achieve? Well, basically, we wanted to have a very clear and concise understanding of all of our optics as they are used throughout our ballparks. And we're using Grafana here to illustrate all of the information so that we have actionable information and so that folks can understand exactly where the problems are and take action to fix them. So in this dashboard, what you can see, or what I'm showing here, is that there are a set of control variables. These are drop downs that would allow us to select, for example, which ballparks we want to look at or which devices we want to look at. And here in what I would call the scope, we can see how many devices we're trying to show here. And in this case, this would be all of our ballparks and all of our optics. And right away, we can get a high-level understanding of the impact of issues. For example, we know right away that we have 3 optics that are in an alerting state and 28 that are in a warning state. So we can kind of understand, how bad is it or how good is it right now. And then in terms of actionable metrics, what we're trying to show here is the devices and the interfaces that are affected so that we can dispatch people and resolve the issues. So right away, we're talking about actionable metrics because we understand exactly, what site it's at, what role the device has, meaning some network devices are used for different purposes in the ballpark, and we can kind of isolate or identify, specifically where these issues are. Some of the content here that has been fuzzed out is actually the host name, the interface name, and the interface description. And it's the interface description that really kind of keys into, what area of the ballpark might be affected, whether it's a video camera or something else. And then finally, in this section of actionable metrics, we're looking at the receive power over time so that we can, observe any trends that we might have. And again, the information here that's been fuzzed out is the device name and interface with description. So again, what we're trying to achieve here is a quick heads-up display so that somebody can look at this and very quickly identify the problems in our network and take action. So a little bit about me quickly. My name is Jeremy Schulman again. I've been in the networking industry for about 20 years. I've held various roles over that time. I was originally, when I got into this industry, I was a software engineer. I've had sales and systems engineering roles, and now I'm back again doing software for specifically network automation. I've been doing this for almost 10 years now. I got started back in 2012, uniquely focused in the space. And I also do a bit of open source and community type engagements like this. So thank you again to Nanog for allowing me to present this topic today. So for our agenda, I'm going to talk about what it took in order to build this type of a system. The things that motivated it, the challenges that I faced, the building blocks and the architecture, and then how we put it into production. My goal here is that by the end of this presentation, you'll have a really good idea of what it takes to build this type of a system. And then ultimately what I've done is I've provided all of this code in the open source. So if you want to give it a shot and play with it, you should be able to download it and try this out in your own environment. All right, so why did we do this? In our world, we have all of these mostly video feeds, or a lot of video feeds, and everything's connected through optics. And in these environments, these environments could be not temperature controlled, so you have a lot of heat and dirt, and it's a ballpark. So looking at the quality of our optics and understanding if there's any issues could relate to any kind of video problems we may occur. So we want to make sure that our optics are healthy. And this is probably a general problem anybody has with optics in a network. Optics tend to fail over time, depending on the environment. And so, this is something that we would want to keep ahead of so that we can figure out what's going to happen and fix it, when it's getting bad. So this is, a key thing. And when I talk about action, action requires context. So we want to understand where the problem is occurring. The context is often referred to as metadata, or if you're familiar with storing data into time series databases, sometimes they call those tags or fields. But the context is what allows somebody to pinpoint where a problem arises in the network. And so in this particular case, the context data would be, the name of the device, the host name. For us, the role of the device. The role for us has specific meaning because some of our devices are used for specific purposes. We might have a role called Hawkeye for a device, which means these are where all of our Hawkeye video monitoring feeds are coming into. And so a Hawkeye system, it may be more important to monitor than, say, another type of networking device. And so having that context information to key into allows somebody to really zoom into the specific data that they want. Again, we have other types of context like the site, the interface name, the interface role itself, and then the interface description actually turns out to be very useful because the people who are looking at this dashboard are not necessarily just the network engineers. The people who manage and monitor the operations at ballparks may also be looking at this, and they know the interfaces by the descriptions that are associated. The most challenging aspect, though, really is synthesis. Action requires synthesis. And what I mean by that is the network devices give you, values. For example, the temperature of a optic or the receive power is a value. But what we need to do is we need to synthesize or transform that value into a status. And if you're familiar with optics and how the optics present themselves in terms of monitoring, there are a series of thresholds that exist for each optic, and each optic may have actually a different set of thresholds depending on the manufacturer and the speed. So they break those thresholds into 4 categories of either being, an alert and a warning if it's too high or if it's too low. And so in many cases, we need to take the value and compare it to the threshold to achieve the status, because ultimately the value doesn't necessarily help the user immediately key into what the problem is. They want the status. They want to know if it's in an alerting state or if it's in a warning state, as shown here from the dashboard. And to achieve this kind of synthesis may actually require executing more than one command on a device. For example, we might not want to include device interfaces that are down because in those cases you would get false positive errors. So you might have to do a command to say, well, show me only, first find me all the interfaces, look at their up-down status, and then only look at the transceiver values for the interfaces that were up. But this type of synthesis that needs to happen is pretty prevalent throughout networking. We call this network knowledge or domain-specific knowledge. But there's lots of examples of this problem. We can get values from the device, like a BGP neighbor state. You can see all of those neighbor states. You can see the OSPF neighbor states, and these are all their values. And then you could even look at, a specific vendor and say, well, what is the status of my multicast? And they have all these wild flags. And as a network engineer, you have to look at all of these values and synthesize them in your mind to say, well, what is good or bad or healthy or expected? And we turn those values in our brains, we turn that into status. And this is what's really, really hard to do. And this is what's really motivating, in particular, the optics case. But the point of this slide is to really show you that the need for synthesis is pretty much everywhere in networking. The other element that we needed to do is track information over time, because sometimes when we're looking at values, we look at the buildup of whether it's trending up or trending down, or what those values are over time, so that if we had to go back in time, we'd have that data so that we could understand what was happening either an hour ago or 2 hours ago, and see trends so that we could perhaps get a better understanding of what's happening in the environment and why we're seeing those issues. So health tracking over time is an important element of any kind of health monitoring system. So in building, this type of a system, it's important to understand that this is actually kind of hard to do, and I wanted to take a few slides to explain challenges that I faced when building this type of system. First and foremost, data acquisition is really painful. As a network automation engineer, trying to pull data out of devices is really hard. It's like trying to get coal out of a mine, like the miner there, because there's really no vendor consistency across our network vendors. The challenge that we face: some of the vendors have a structured API, others require SSH, and CLI text parsing, which is very painful to do. Some APIs support structured output for the commands that you need for your particular health monitoring use case. Some of them don't. Some of them support APIs for a particular version, but not all versions. And in a large estate of equipment, you might have different versions of operating systems running across your infrastructure. Another problem is, in the case of the optics, in the case of the optics use case, some vendor operating systems would actually do the synthesis. They would tell you whether or not an interface was in an alert or not in an alert state, and others just give you the data and require you to perform that comparison. Some vendors I found say that they will do that synthesis, but I found bugs, and so you always have to be aware that some CLI outputs have bugs, and you need to consider that. And then finally, there are no standard MIBs for this particular use case for doing optic measurements. So, again, data acquisition, harvesting the data from your network and doing it in a vendor, agnostic way is very, very hard to do. And a lot of effort is generally spent, doing this one step, just getting the data so that you can then process and use that information. And then generally speaking, the synthesis problem is very complex. This is because networks are distributed systems and we don't have a total span of control. As an operator of a network, there are devices in our network we don't control, like the connected hosts. Those could be our customers or our users, for example. We might be connecting to service providers, and they offer themselves as critical dependencies to our network. So if that interface to a service provider goes down, or if we have issues to service provider networks, understanding the health of those systems is hard because we don't control them. We can only see the effect from our side of the link, so to speak. And really, the vast complexity of dealing with networking is that we have all of these networking protocols that interrelate with one another. We have routing protocols and switching protocols and all sorts of protocols. And depending on the type of service your network is trying to achieve, for example, EVPN is a very complicated inner set of networking protocols, and troubleshooting that is very, very hard to do, in a large enough network. And then, finally, or another aspect is as the businesses change the requirements of the network, we have design change that happens. And when those design changes happen, we have to, make changes to our network. So we have, change in the network affects the decisions that we make for those protocols, and getting a sense of what our network is doing, the health of that network is hard because of change. And then I always like to say, we always have to account for bugs in vendor products because we find them and then we have to kind of code around certain bugs in products. And that in itself creates a level of complexity. So just having all of this data is really hard for networking teams because there is an overwhelming amount of data. If you thought of all the show commands that you do, and then in your mind try to synthesize all that into some linear pattern of information, it's really, really hard because it's an overwhelming amount of data. And so, it's critical to take that data and synthesize it into information, and then knowledge, and then ultimately wisdom. And what does wisdom really mean? We have vendors coming out today talking about machine learning and AI, and what they're really trying to say is they're trying to take all of this data, look at it over time, and get an understanding of what your network is doing based on that data to give you a higher order of synthesis so that you can take action and do something useful. But, will we get there? Time will tell. Another big challenge I had was with existing products, using those products. So these are my experiences. Your mileage may vary. A lot of the commercial products out there, or even open source projects out there, they are not able to accept or assign context data. And what I mean by that is like assigning a role to an interface, for example. Some products allow you to assign metadata, some products don't. Some products, most products, in fact, almost no products support synthesizing of the data. I've started to see a few out there, but most of them don't synthesize data like this. A lot of them don't normalize vendor-specific data, meaning if you get, interface statistics or optic information, pulling that data out and normalizing it into, say, alerts or warnings is not something that they do, or even taking the values and normalizing it into a set of information. They don't normalize data. They'll present the data, but they don't normalize it. A lot of products, are still just SSHing into devices. They don't take advantage of APIs. As somebody who's programmed against APIs, I understand the challenges with APIs changing over time, and it makes it difficult for vendors to pull that data. But then they're dealing with SSH changes over time. So what I found is a lot of products are just simply fancy SNMP collectors, and then they try to figure out, well, which devices, what is the vendor or the model of that device, and try to map in SNMP MIBs to pull out the data. But it's challenging because, every time we upgrade a NOS and the CLI changes or there's MIB changes, you'd have to update those SNMP collectors and deal with, the change of the operating systems. A lot of these products aren't not built to integrate with other inventory systems. So in the sense, a large part of what somebody like myself would have to do is do that kind of glue coding to integrate those systems together. Some types of products, will perform snapshotting versus constant polling. And if your network is large enough, is pretty big, and depending on what those products do, taking a snapshot takes a long time. So you're not getting that near real-time value that you need. So there's been a lot of, advancements in products over time, but still, these issues present challenges to try to build a near real-time health monitoring system. And then you get into what I would call the Firefighters Paradox, meaning, a lot of times you don't know the tool that you need until you're presented with a problem. And when you're presented with a problem, then perhaps your house is on fire and you have no time to build that tool to solve the problem. It's like saying, as a firefighter, I need to go buy a new fire truck as I'm rolling out to go fight a fire. You can't do that. You don't have the opportunity to do that. And a lot of times people don't know what health monitoring they want to do until they're presented or surface a problem in their network. And these tools take time to deploy, build, support. Even a commercial product, you have to support it, and so there's a lot of time and money that's put into monitoring the health of your network. And so what I'm always looking for is better tools or better technology that reduces the friction from the point of going oh my God, I have a problem in my network and I need a monitoring tool to, keep an eye on it for the next time and get that done quickly and efficiently so that in the future we've got that tool in our, at the ready. You can't look at a problem and say, well, gosh, I had this problem and it's going to take 2 months to have a solution to that problem, because you might have that problem again, in a week or in a day. So what I'd like to do now is talk about how I went about kind of taking technology that was, both open source and put it together in a way to create this solution. So this is really what I would call architecture, the software components that I used. And before I get into the specific pieces of technology, I wanted to talk about the parts of the solution, right? For me, what I looked at was 4 building blocks. The first was you need an inventory source of truth. It can be a spreadsheet, it could be commercial product, but this really is a database that tells you these are the devices in my network. These are the systems that I'm going to monitor. And at the minimum, you need to know, the management IP address, the host name, and this is where you're going to get your context data, the device role, the interface role, what site it's in. This is essentially that data repository. You have to, and you need one, because a health monitoring system will extract that data, and maybe even periodically extract data because maybe that source changes, because it's what's going to be used by the collectors in order to figure out what they're supposed to be collecting. Now, the metric collectors, in my case, these are the pieces of code or the product that would go to the devices and collect the information and synthesize them into normalized metrics. So in this particular architecture, I'm synthesizing and normalizing the data as close to the metal, so to speak, as possible, from the device itself. I suppose you could, pull this data from some other system that's already collecting it, but the goal here is getting the device-specific data, in the form of that is specific to that vendor or operating system, and knowing its source, the vendor and the operating system, transforming it and normalizing it. Because, in this case, what we want to do is we want to put that data into a time series database, and we're going to use the context information as the tags or the fields. And then the values that we're going to store are the normalized and synthesized values into that time series database. And, we want to put it into a time series database because we want to have the ability to look back over time for various reasons, or stretch out our view of time. So maybe we care about, only the last hour of a time slice, or maybe we want to aggregate data, in terms of, only the last, 30 minutes. But there are many time series databases that allow us to store that data and perform queries of that data over time. The challenge here, though, is that most time series databases, they have their unique query languages. So, much like a CLI or an API in a networking device, every time you make a decision to use a piece of technology, you're kind of locking yourself into a time series database and the query language that it uses. And you may also find that you might want to use multiple time series databases, because each of them offers slightly different, benefits. And then ultimately, you need some kind of visualization technology that will pull data out of a time series database and allow you to create, the charts and the graphs and the tables and all the widgets so that you can visually get the information that you want. The challenge here, though, is there's generally a tight coupling between the visualization, widgets and the database. So in terms of Grafana, for example, they give you a set of visualization widgets, but the query that you need to execute to get the data to populate those widgets, that query is specific to the time series database. And so, just to give you an idea of your choices, and this is just a sampling because there are many more than what you have here, that for each of these architectural building blocks, there are choices that you can use, or you can use multiple choices here. I didn't find anything better than Grafana when I was doing my dashboard visualizations. I'm always on the lookout for really cool visualization technology, but I didn't see, more options for Grafana for the use cases that I had in mind. But when I built the optics monitoring, this health optics monitoring, the choices that I made, I use Netbox for our inventory source of truth. It does a very good job of allowing me to store all sorts of types of context data. The metrics collector, what I ended up doing was writing a framework that would allow me to collect the metrics and then synthesize them and normalize them, as a piece of code. I did look at using Telegraph originally. So Telegraph, going back a slide, is is an open source project that has a lot of really great capabilities to do something similar to what I wrote with this Python framework, but it didn't offer me the ability to do normalization and synthesis in the way that was important for me. So I ended up writing some code It's out there in this repository, and then I've broken out specific apps. So there's an optics app for NetPaka, and there's a couple other ones out there in this repository you can take a look at. I chose to use the Influx database for my time series data, and I chose to use Grafana for the visualization. So now that you know the kind of the building blocks and what I used, I'm going to talk about how I deployed this into our network and tried to address some of the issues in terms of scaling and reliability. So what this slide is showing you is kind of how I deployed the Docker containers that provided each of those architectural services. So we have our netbox. It's a Docker container. It exposes, port 443 for an API. So, that's a Docker container, could be running on, all of these Docker containers could be running on different servers, physical servers, so we can kind of balance out the load. Each of the NetPaka collectors was a Docker container. And I'm going to talk about how I sliced up the inventory of our infrastructure in the next slide. But ultimately, what's happening in this kind of block is periodically I would go and I would fetch the inventory from Netbox, and then I would restart my collectors, because there could be changes in our network where certain devices may go offline or come online, or maybe we wanted to refresh which interfaces are being used or not used. So I built in this kind of periodic refresh of going to Netbox, figuring out what we needed to collect, and then restart the collecting environment. But those collectors are what goes to the devices, whether it's by API or SSH, and pulls up the data. And then NetPaka then sends that data to the time series database. NetPaka was built to support, Influx and Circonus, and a couple others are in the works. But the NetPaka framework can emit the metrics to different sources or time series databases. In this case, Influx was running on another port, on another system, and I also had Grafana running on that same system. So in my deployment environment, I had these three different servers running in this kind of configuration. But scaling out the collectors, that's really the kind of larger issue. If you have a large network or a small network, it's about the collectors, like, where do you place them and how do you scale them out? You could put collectors on physical servers. You could even run them in the cloud if you have access to the devices from the cloud. And each collector would process a portion of the overall inventory. So one decision was, well, do I make a collector per device? Well, if you have 5,000 devices, that's too many collectors. Do I put all of the devices in one container? Well, if you do that, you might consume too much memory or too much CPU. And so the idea was to decide, well, how do I want to slice and dice my inventory? And so the way the NetPaka control files work here is you can decide which devices you want to include in a collector container based on the criteria or the metadata of the devices. Like I could say, put all of my core switches in one container, put all of my Hawkeye switches in one container, or I could say, put these 5 ballparks in one container, put these other 5 ballparks in another container. So having that choice is important, because you'll need to figure out, when you build something like this, how to scale out the use of, or the resources that you're going to need in servers. And then, of course, you're going to need a way to measure that, because it's a bit of art and science to figure out resource usage. So because I'm using containers, there's a tool out there called CTOP, which will give you the runtime information about the containers that you're using and how much CPU memory and even how much network bandwidth they're using. So I needed a system that would allow me to do this type of slicing and dicing and then measure it so that I can scale this the way I needed to. Another aspect, rather than just using, the containers and slicing them by their metadata, was by slicing them by their actual monitoring purposes. For example, I might have an interface optics monitoring health set of collectors, and could be a container image. I might want to have a different container image for monitoring my routing protocols. I might want to have a different type of container image for monitoring my multicast flows. And again, the controls here were allowing me choice about how I wanted to deploy the collectors in my environment. And in each of these cases, these would be a different set of collectors, but the overall framework would be the same, meaning, going out to the devices, collecting the data, parsing the data, synthesizing the data, and sending them out to a time series database. The framework remains the same. The only thing that's really different here is the unique bits of code to collect and parse. So, does this sound like something you want to try it out? It's important to understand when you're looking at the effort you put into network automation. What is important to you? What is important to your business? I always ask the question, is the juice worth the squeeze? Meaning, if you have to put a lot of effort into something, is it worth it to your business? Because ultimately there's a price a business pays for, the time and effort and money that's put into building these systems. And I feel that the juice is always worth the squeeze when it comes to these network health monitoring systems, because the hardest problem is trying to fix or identify or resolve issues as they occur in your network. Going from the, oh crap, something's wrong in our network, to, hey, everything's fine again. Reducing that time is exceptionally valuable to businesses that need to have their networks up, like us. And the idea of having proactive health monitoring is always about looking at data that is a precursor to other problems, like optic health, for example, so that you can get ahead of an issue before an issue actually manifests and your customers, the users of your network, report the problem. So getting a sense of proactive health monitoring versus reactive health monitoring. The proactive is what is an element of what businesses always want. I would submit that people always want to be proactively monitoring the health of their network to prevent issues before they happen. But many times it's very hard to do, based on the context and the synthesis that needs to go into, mining that data and providing valuable, insights. But once you do it, the juice is worth the squeeze. And again, the other point that I would, summarize with is building these systems is hard to do. I mean, this is not, a point and click type of solution, and it generally does require a lot of do-it-yourself custom software, because some of the things that are important to your business may not be the same types of things that are important to other businesses. If you don't use Multicast, then Multicast health is not important to you. But if you use Multicast, then Multicast health is very important to you. And so, what I've said before is that building these types of systems requires, two parties to come to the table and work together. You need a network subject matter expert, somebody who understands, well, what are all the commands that I need to run? What pieces of data are important? And what does that data mean? That's the network domain knowledge, the synthesis, that they understand in their heads, working together with a software subject matter expert to turn that knowledge into software so that other people can have that information available to them, and they don't always have to, call the networking team or open a trouble ticket, And ultimately, at the end of the day, I believe that most people want these network health monitoring systems so that everybody has access to that information and can take action without waiting for somebody to, service a trouble ticket. And even though this is hard, even though it's going to take a lot of time, don't be daunted. Start small. Build your experience over time, and try to take advantage of some of the software that I've shown in the slide deck, and others that are going to come out. There's constantly people working and building software in the open source or commercial products. So it will get better over time, but don't just sit by the sidelines and say, well, I'll wait. It's always great to get started, start small, and build your skills over time. And so with that, I'll open the session for questions and answers, and let's see how this goes. Great.
Well, thank you very much, Jeremy. We have a few questions that came in during the talk. So first, do you have any comments, or what is your experience with the vendor support regarding telemetry DOM pads?
So I think the question is implying streaming telemetry when they use the term path. I'm not certain, but I think that might be what they're getting at. So it turns out that for my network infrastructure, we're not using streaming telemetry as of right now because it's something that we're investigating, but it's not something that I'm taking advantage of right now. I've looked into it, and there's different vendors that kind of have a different approach. So some vendors, will stream everything all at once, and other vendors, you have to tell the systems what you want it to stream. And so that kind of gets into its own type of management. But I haven't really dug into it a lot. The sense of it though is that's where we're headed, and any kind of system that I'll be building or interacting with, I definitely look forward to using streaming telemetry because it's it changes the dynamics of the equation. Meaning you're drinking from a fire hose rather than begging for data, but you still have to synthesize it, normalize it, and send it off to streaming database. But it does change the dynamics a little bit.
The next question sort of fits in with that. Not so much streaming telemetry, but events, things like SNMP traps. So the system that you built relies mainly on polling. How does it either work with or replace fault detection?
Yeah, so it's a good question, and to kind of take a step back, there are good tools that do good things, and the goal, for somebody like myself is not to try to invent one piece of technology that is the Sauron's ring of network monitoring. We have a lot of products out there that do great things with, event handling and processing and root cause analysis. And if we perhaps have a product that does that, I'm not going to try to reinvent that into anything. The goal that I had was specific to taking data, synthesizing it, normalizing it, putting context, and sending it into a time series database. If I have another system that does that same process in a way with events, then I might use its system natively, depending on its user interface, or I could pull data from that system and throw it into the time series database as a benefit. But again, I have to look at is the juice worth the squeeze on that kind of a thing. But again, try to find tools. I always try to find commercial products that do the thing that I want because, I'm one person. I can't write code for everything. And I try to, spend my time gluing things together in a way that's valuable to the business.
Speaking of some tools that are available to you, how are you able to get Grafana to notify you rather than somebody having to look at graphs all day? And related, can you do any comparison between Grafana and Nagios XI?
Okay, so those two separate questions. The first is that Grafana and its ecosystem does have an alerting environment, so you can set up alerts based on thresholds and criteria that you might want to do. I actually haven't plumbed the depth of that too much. The kinds of users that I've got sometimes like to log in and look at something to get a visual, and lock into it. But getting alerts sent asynchronously, and for us, for example, sending it into a chat, like a Slack chat channel, is of high value. So it does support it. It isn't something that I've plumbed the depth on. The other question was on Nagios IO, and I haven't really dug into it, but now I want to. So it's thanks for offering that up.
On the network itself, approximately how many optical devices are you monitoring, and what have you found to be the compute resources required for various components of the system?
For optical monitoring, in this particular use case, The first dashboard kind of gave you a sense of how many devices, that we're hosting optics for ballparks. Our estate of infrastructure is much larger than that, but just for this scope of this, I can't recall the total number of optics. It's a very large number. And then this is why we go into how do I chunk up the collectors into Docker containers so I can scale out the collection processing. From an impact on the devices themselves, it was negligible. I didn't really detect any kind of, I wasn't hammering the boxes very hard for it to be impactful. I'm not sure if that answered the question, but that's what we were doing.
The next question is actually a little bit related to that. How are you getting data into your system? Is it via SNMP? Is it via an API? And since you're talking about time series data, do you have trouble getting all this data that you need within the required interval?
Oh, okay. So again, two different questions. The collector software that is talking to the device is written, to take advantage of whatever the system offers. So if for us, for example, we have NXOS systems, some of which have APIs, like NX APIs, and some, we require SSH. So depending on the collector and the device that we're talking to, that's kind of the realm of what the collector software does. There were cases in which I actually did use SNMP to get the data out because in one of those cases, it was the only way for me to get the data that I needed. There was no API, and I don't believe even the SSH commands were a cogent way of getting it. So it's a combination thereof. We should always try to pick the right tool for the right job. Getting it in within the interval is an interesting question because it depends on what the interval is for what you're looking at. Sometimes you want a high order interval, like every minute. In some cases you don't need a high order interval, like maybe every 5 minutes is fine, or maybe every 15 minutes is fine. So that's very application specific, or aspect specific.
Unrelated to the presentation, but an interesting question nonetheless. Someone wonders, what is the bandwidth you see coming out per multicast stream, and what multicast application do you use?
Yeah. So one of the things that I also had to write was a multicast health monitoring system. And for us, what we were really going after was not so much the bandwidth of the multicast stream, because we use a different tool for that. We could use net flow traffic, for example, to monitor that aspect. But what we cared about was the health of the multicast flow itself, meaning, did we have a multicast flow active that there was, a source and a receiver, and data was flowing across it, or did we have a source for a destination group, but we had no receiver, so it's an inactive stream, or did we have flows that were in a stuck state, which would be indicative of the flags that we were observing? For example, if for whatever reason there was an attempt for a receiver to try to join to a multicast group, and it was in some transient state that should have automatically changed it over to an active flow, but for whatever reason it didn't. Finding these stuck flows, which would then say, oh, this is why perhaps the video feed stopped. That's what we were really going after. It wasn't so much the bandwidth of the flows themselves, because again, we would use something like NetFlow to monitor that.
Okay. We're just about out of time. I had one question that I wanted to ask. You developed NetPaka, and it seems to do a really great job at synthesis and structuring data. I'm just wondering, what sort of advice would you give to the community of how they can evaluate what sorts of tools that they can use for data acquisition, or even if they would want to build their own?
Yeah, it's a really great question, because there's no real right answer. I always say that there's a right now answer. It depends on the individual, their skill set, where they are with trying to learn something new, the environment that they have, like can they ask questions to other people, give them help and so forth. There's a lot of great community in our industry supporting and educating in network automation. So find something that works for you, and don't let other people be judgy about it. If you use Ansible to do everything, and it works for you, that's great, and even if there is quote unquote a better way that somebody else might know, don't let them get you down about that. Use what, if it feels good, do it, right? Use what fits your brain. And as you keep, experiencing and using new tools, you'll develop better skills. And then you'll find that perhaps there is a better way. Maybe I should be doing something more sophisticated that I thought was, unreachable for me a year ago, but now it's in my wheelhouse. And just keep pushing yourself and learning, because, in our industry, that's just the nature of the game. You're always going to be learning something new. And in the profession of software development, which people are getting into, even though, they're not going to call themselves developers or engineers, which is fine. They're using programming as a tool, but it's a never-ending journey. I still learn something new every week in Python, and I've been programming in Python for 5 years. So.
Okay, well, we're out of time for the question that we were unable to get to, as well as questions that people had but they didn't ask. What's the best way to reach you after this presentation, Jeremy?
Everybody's, welcome to reach me out. Hit me up on Twitter, at Network Automaniac. My contact is on the slides, which you can download, as well as with all the other links to the NetPaka stuff. So yeah, just hit me up on Twitter anytime, and I'm happy to answer questions as I can.
Thank you so much.
My pleasure. Thank you for having me.